All right, so let's discuss some of the geometries with the radius of protection. The IEEE 5.3 actually stops right there. They give you the formulas that will help you calculate the radius of your sphere, but they leave it up to you to roll it around your substation and figure out exactly where it's going to go and what equipment it's going to intersect with. It can be done if you know your strike distance, the height of your mast, the height of your equipment. You could find R if you knew these values. You knew the value of your strike distance, knew the value of the equipment height, and you knew the value of your mast height. You could calculate R. But that's just not a very realistic thing to do. It requires the designer to take a lot of time and go through just hours and hours of geometry calculations. Well, a gentleman by the name of Jeff Camden wrote a paper a few years back, and he figured out the geometries for us, and he came out with some geometric formulas for some very common configurations. So rather than just knowing S and rolling the sphere around to test everything, you can actually calculate the protection zones provided by your masts and wires with his formulas. For example, here's the formula for a radius of protection provided by a mast. Now you can see here that we have two different formulas. If the mast is greater than your strike distance, again, as the mast height gets taller and taller and taller, it doesn't affect your radius of protection. Again, we're not going to go too deep into the formulas. Just wanted you to see them here. Same thing for a wire. This is the plan view for a wire. If you can imagine your sphere rolling into this wire and providing some level of protection as it goes around this wire. Again, it can't go through the wire. It has to go up and over it or around it. Provides this level of protection for your equipment. Well, it looks like it doesn't provide a whole lot of protection. You're wondering, well, how many masts and wires am I going to need? That seems like I'm going to need them all over the place. Well, there's some certain combinational effects that you can take advantage when you're using two masts or two wires that are close together that provide even more protection. Let me illustrate that here. Here you have two masts that are close together, and they, by themselves, provide this light gray level of protection. However, if they're close enough together that the diameter of the sphere, that the sphere cannot fit between them as it rolls through them, then it won't go through them, and instead it'll go up and over them and provide you this extra bit of protection. Again, for that to happen, the two masts have to be at a distance from each other that is less than the diameter of that sphere. That provides additional protection. Well, what about two wires? We have two parallel wires, again, that are close enough that the sphere can't fit in between them, then everything between them becomes protected as well. So you can see from this plan view the protection provided by each wire, and then the dark gray area is the additional protection provided by the combinational effect of having two wires close together. If you can imagine the sphere rolling around and it can't fit between these two and has to go up and over, you can see that this particular configuration can be very powerful. And this is actually what's commonly used when you have a lot of inline distribution bays, where you have from a high side to a low side, and it's all in a very straight line. You'll often see a dead end on the high side, on the outside, running a wire to one of the distribution bays, and then again on the opposite side. And again, they'll do this because of the amount of level, the level of protection it provides for just adding two wires. Can everybody see what the section view to this is going to look like? It's going to look something like this. Again, if the wires are close enough together that the sphere can't fit in between the two, it'll roll right over and provide this additional level of protection. All right, so let's say you have three masts. Well, if you have three masts, it's the same thing. You could do your calculations based on two masts three different times. You'd have to do that for this side, and then this side. So again, when you do each of your two-mast analysis, you're going to get this bonus level of protection shown in the dark gray area. But then there's one thing to consider. If the masts are far enough apart that the center of the sphere begins to actually dip into your equipment height, then you have to consider that. The bottom of the sphere could provide a level of an unprotected area, which is illustrated by this white circle here. So, and it's very rare cases. It has to be such that the three masts have to be close enough together that you get the combinational effect, but far enough apart that the sphere actually sits down into them and digs into your equipment height. Again, very rare, but it is something to consider. And we have the formulas again to calculate that value. What about 3 wires? Same thing with 3 wires. You do the same combinational analysis, and then you must consider that a sphere could be sitting on top of the 3 wires, and the bottom of that sphere could dip so low into your equipment height that it could provide an area that is unprotected. And again, here are the formulas to calculate that. All right, let's now discuss failure rate. Again, this was one of the shortcomings of fixed angle. It can't really provide any sort of reliability analysis. Everything was either protected or not protected. Also, we must consider that lightning is a probabilistic phenomena. We don't know exactly when and where it's going to strike, but we can use probability to explain how many strikes we can expect in a particular area over a given amount of time. So to calculate failure rate, first you want to determine what strike distance would have resulted in protection. In other words, how much, if we have an area that's unprotected for IS, what stroke current would have protected it? In other words, how much more does that step leader have to reach? How much do you have to increase that strike distance by so that it would reach? Again, the reason we want to do this is to find what is the window of stroke currents that if a step leader forms in that area would create a return stroke that would travel through the equipment rather than being able to reach a mast. All right, so going back to this example, we see that a certain stroke current that results in a strike distance of this blue circle leaves this area unprotected. But if the stroke current was just a little bit larger, as illustrated by this red circle, that area would actually be protected. So this is that window of stroke currents between this red circle and the stroke currents that cause this blue circle that we're worried about. Anything greater than that red circle, we know it'll be able to strike the mast and everything under here will be protected. Anything less than that blue circle, we understand the insulation will be able to handle, and so we're not really worried about that. All right, next you want to calculate the probability that the stroke will actually fall in that current range. Again, large enough to break down the insulation and cause flashover, but smaller than what's large enough, what's necessary to reach a mast or another grounding electrode. And we have formulas for that. Then you need to measure the area of that unprotected region, and then you can then determine the number of expected strokes in that area. Well, how do you do that? Well, we have a isochronic map from the National Weather Service that'll show you how many lightning strikes you can, how many annual thunderstorm days you can expect in your area. So for Atlanta, for example, we could conservatively say 60 strikes a year. That would be our value of T, and we could plug that into this formula, multiply it by the area that we've left unprotected, and find out the number of strokes that will occur in that area per year. And then you just calculate the failure rate from this formula. Again, you know the number of strokes expected in your area, your unprotected area, per year, and so you can tell how many years it'll take before you get a failure. And usually in our industry we like to say that 1 failure every 100 years is acceptable. All right, so now to do your calculations, you have everything you need. You have your formulas from IEEE and your formulas from white papers such as Mr. Camden's paper. You could get all your equipment information such as your conductor data and your BIL, your structure heights. You gather all that information. Again, go back through your formulas, get all your formulas, and find your old geometry textbook from high school. Gather all your formulas, visualize your sphere, maybe trace it out on a plan view, and perform your hand calculations. You can do that, and I've actually done that here. And this, you can see, this is an analysis of a MathCAD analysis of 3-mast configuration. You can see that's 3 pages of formulas. It takes a very long time, It's very easy to make a mistake. It's just not practical sometimes. So what we've done, we've decided to make a website that'll calculate all these values for you so that you don't have to worry about mistakes or sit there and plug and chug at formulas over and over again. On behalf of Burns & McDonnell, I'd like to thank you for watching. I'd also like to encourage you to download the Rolling Sphere Tool Guide from the website. It breaks down all of the formulas and variables in great detail. If you still have questions, feel free to contact me at bpatel@burnsmcd.com. Thanks for watching.